Can you hear this? In every factory, every day, every night, invisible heroes working all time. That's not a sound effect, this is pneumatic actuator doing its job. Today we're going to program pneumatic actuators in Codesys environment based on Finder OPTA PLC. Let's get started. Remember to hit the like button under this video and subscribe to Control Byte YouTube channel to be informed about our latest videos.
Before we start programming in the Codesys environment, a few words about our setup. Look, we have two pneumatic actuators here, which are connected to two pneumatic distributors. One of these distributors is a 3-position distributor with 2 coils. Meanwhile, the other distributor is a solenoid valve with 1 coil. If I manually trigger this solenoid valve, look, the actuator extends. This will be actuator number 1. This actuator is equipped with 2 limit sensors, the home position and the extended position. Similarly, we will control actuator number 2 using this 3-position distributor. Activating the coil on the left side causes extension, while the return is triggered by the second coil. The brain of our system will be the Finder OPTA controller on Codesys. This controller is equipped with Codesys runtime, and we can use the Codesys environment to program this controller. The task of this controller will be to read signals from the limit sensors of the base position and the working extended position. Additionally, the controller will power the coils, triggering operation for the actuator with a 3-position distributor and for the actuator with a 2-position distributor. As you can see, the logic of operation when controlling these distributors is slightly different. Here, after triggering the operation, we can stop in an intermediate position. Actuator, however, for the 2-position distributor, removing power from the coil means returning to the base position. The key in this application is the use of an expansion module for the Finder OPTA controller equipped with SSR outputs, which are transistor outputs with a load capacity of up to 3 amperes. With such an SSR module, we can very dynamically control pneumatic systems and coils in hydraulic solenoid valves, which draw much higher current, even up to 3 amperes for a voltage of 24 volts. If you want to control coils with higher voltage, for example, 230 volts, you can use relay outputs. Okay, now you know how our system is constructed. Now let's move on to mapping variables in Codesys. Let's start with mapping. I already have the Codesys project open. If you want to see how to create the first project, how to add a controller to the project, and perform the initial configuration, I refer you to the video we recently published. Click on this tile and see how it's done from scratch. Now I will show you how I perform the mapping on an already pre-configured project. I am moving to I/O, inputs, and outputs for the main CPU unit, which is equipped with inputs and outputs. To the inputs, ranging from I1 to I4, I assigned variables that I named according to the sensor naming nomenclature, namely B1.1 and B1.2. Well, this is actuator number 1, the actuator at the bottom. This actuator has 2 sensors, a base position sensor and a working position sensor. Look, if I now extend this actuator, the sensor for extension B, 1.2, has taken the value true, while sensor B, 1.1, has the value false. If I release this solenoid valve, the state changes to true for the base position sensor and false for the extended position sensor. Similarly, for actuator number 2, B2.1 is the base position, the retracted position. If I want to extend actuator number 2, which is the actuator on top, I need to control the appropriate valve. And see, at this moment, sensor B 2.2 is active. This is the sensor for the extension of the actuator. Now returning, sensor B 2.2 is in the false state, and sensor B 2.1 for the base position of actuator number 2 is activated. Variables that will power, activate the solenoid coils, I assigned to the SSR module, the output module. Look, we have 3 mapped variables here, named Y 1.1. This is the solenoid valve with 1 coil. The Codesys environment has tools necessary for every automation engineer during startup, namely function of forcing. Look, now I will force the coil of the first solenoid valve. I go to debug force values, and look, the actuator extends. I have information about forcing here. I turn off the forcing. And the actuator returns. Similarly, I can check the operation of the second actuator. We force it, the actuator extends. Now we set the value to false here and power the coil number 1, which will generate the return. That's okay. The actuator returns. This means that mapping our variables to specific output channels and input channels for sensors is working correctly. We disable forcing so it doesn't interfere with our programming. And now we move on to the programming part. We will start with the ladder language. Okay, let's write a simple program in ladder that will allow us to control these actuators using a defined sequence. We will start with the standard start-stop circuit. Here, we will choose a set-reset flip-flop with dominant reset. We define it here in the variables for the ladder. Now let's introduce the set condition. I will refer here to the button located on the controller and additionally a trigger. Okay. Similarly, the reset condition. Here we will define an additional contact that will check if the variable global X state start will be in a high state. This variable will store information about the sequence status. And using a button on the controller for testing purposes, we will start this sequence. Okay, the set reset flip-flop for the variable X state start is ready, turning on and off with a single button. Now let's add another network. And at this point, we will define the 0 step, initialization step. In each step, we will refer to a variable that will store information about the current step. We move to the map operations tab. Here, we will use the equal to comparator. And let's define the variable step, an integer type variable. This variable will be used to determine the step state. If the step takes the value 0, here we can still assign the value 0 during initialization. Then we perform the operation on this side of the network. Okay? In each of our networks related to steps, we will use the function move to transition between one step and another. For example, thanks to this move block, we will transition between step 0 and step 10. Between these blocks, we need to insert transition conditions in our system. Typically, this will refer to the start variable and, for example, the base position of our actuators, meaning we query the retraction sensors for the first actuator. Okay? Or once again. And the same for the second actuator. We have already defined the transition between steps. We have defined the transition condition. Now we still need to define the action. I open a new branch, and here I insert a coil from the library. I basically need 3 coils here. Interestingly, I can't use a keyboard shortcut here, but if I drag this coil this way, everything works great. Okay, and the third coil. We can also set these coils as resetting by using the right mouse button, or replace them, for example, in this way from the library. Now we will define the power supply for the coils for this step. This is an initializing step, so all coils will be reset, and voila. We already have the basic structure for step 0. See how easily I now define the next step. It will be step number 10. Here, I insert the number 10. Then in the next transition, I move to step 20. Now, in this step, I power the first coil and check if the first actuator has extended by querying the sensor from this actuator. And that would be it. We have already defined the next step. Now the next step, step 20. And that is all the code we need to conduct the first tests. Now, let's load this configuration into the PLC and see how it will work. Okay, let's go online with the controller. I'm downloading the program to the Finder OPTA controller. Now I switch to start mode. And let's see. We already have a program preview. We are at step number 0. And our controller is waiting for the start signal, which is the button on Finder OPTA. I press the button and let's see. This parameter shows the current step. I press the button and we are at step 10. The actuator extends. Step 20. The second actuator extends. 30th step. The actuators return and the sequence repeats again, meaning the 10th step, extension of the first, 20th step, extension of the second, 30th step, return of both actuators. Okay, you already know what such a program looks like in ladder language. Now let's move on to the textual language ST. For this purpose, I add a new POU Program Organization Unit object, and here I select the structured text language. We can also add a POU underscore et suffix here. Okay. I also define the variable isStep as an integer with an initial value of 0. And now we can write the code here based on the case instruction. Look, we will define each step in the next section of the case instruction, and essentially they will look similar. We check the transition condition. If the variable x state start is in a high state, and we also have in a high state sensors, then we move from 0 to step 10. Additionally, let's refer to the output variables. Coil 1, coil 2 is off, and coil 3 is similarly off. Okay, now let's copy this structure to the next step and only change the reference to variables and the assignment of states for the coils. Okay, let's now check how this code will work. However, before we download this code to the PLC, let's check how these programs are called. Look, here we call the program that we wrote in ladder. I can add the program we wrote in structured text. And right now, we will call two programs that will override their variables. To prevent this, we can, for example, comment out these lines. This networks in ladder language. Okay, we can leave the start-stop system because we also use this global variable in ST language. Alright, let's load this program into the PLC. Great, I am already in online mode. The controller is in stop mode. I can also perform a warm restart to reset all variables. I press start and nothing happens. Let's see. Our program is waiting for the variable X state start. So I need to press the button on the Finder OPTA controller. And look, at this moment we have step 10. Extension of the first actuator. Step 20. And as you can see, our system temporarily froze. I probably mixed up the coil numbers here. So, a quick fix. Okay, and let's see. At the end, we have the return of Y. I click on line. The program is updated. I press start and the first actuator moved. The second actuator started. And we are in step 30, which is the return of both actuators. Again, step 10. Start of the first actuator. Step 20. Extension of the second actuator and return of both actuators. Great. Our code in ST works. As you can see, sometimes you have to be careful with coil numbering. And now let's move on to the next language, which is SFC. We have a new POU object. And here we select the SFC option. Look, SFC language is already prepared for the implementation of sequential systems. Here we have a diagram analogous to the graph set diagram. The init step has already been defined, so we don't need to do anything here. We just need to add another step. It is immediately numbered, and the transition is also already created. See how efficiently you can write such a sequence. Here, we will directly refer to our button, meaning we trigger the sequence with the button. Let's move to step 10, as we described earlier. Here we need to power one of the coils. I click Add Action. I choose Coil that we will power here, and voila. the remaining coils will remain unpowered. Now I check the transition condition, which is the extension of the first actuator. And we can still hear add and return for the second actuator. Okay, this is step 20. In step 20, we assign an action. Powering the same coil for the first actuator, and an additional action is powering one of the coils for the second actuator. Okay. We check if both actuators extend, meaning in this condition, we refer to sensor B2.2. Great. We add another step. Step 30. And here we check if both actuators return. To return cylinder number 2, we need to add an action here that activates the coil, specifically Y 2.1 solenoid for returning cylinder M2. Alright, before we load this program into the controller, let's move on to the configuration of program calls. I need to delete my program in ST now. I can also delete the program in the ladder for now. I add my program in SFC, press the start button to start Finder OPTA and see. At this moment, the init step is already counting the duration of this step. I press the button to start the sequence. And I am in step 10. Extension of the first cylinder. Step 20, extension of the second cylinder, and the return of both cylinders in step 30. The sequence has ended. We are back at the init step. To trigger it again, I need to press the button. Step 10, extension of the first, extension of the second, and the return of both actuators.
Okay, that's all for today. Thank you for watching. Remember to hit the like button under this video and subscribe to Control Byte Automation YouTube channel. See you in the next video.